suppose now it works, right? Okay, thank you. So I'm planning to give an overview of algebraic, the theory of algebraic groups. And my plan, hopefully, will be the following. First, today I will introduce basic notions about algebraic groups. The starting point will be the notion of an affine group scheme. And the goal will be to say that basically if you make suitable assumptions, then such a group functor is actually a group of a matrix group. Then the second talk will be about differential calculus and quotients. This is where we will introduce Lie algebras in particular. Then I will deal with classes of remarkable subgroups, like maximal tori, maximal connected solvable subgroups called Borel subgroups, and conjugacy theorems for these classes of groups. And then, if time allows me to do it, I will I will sketch the classification of reductive groups. Okay, so as you probably understood, I will not be able to prove many results. I will give some hints which are supposed to help you to read some classical references. So what are the references in the topic? First, there is, of course, a book by Borel, which is called Linear Algebraic Groups. There's the book by Springer, which is has the same title. And also, there's for the algebraic group from the affine group scheme viewpoint, there is a book by Waterhouse, which is an introduction to affine group schemes. So basically, today the reference is this book, the third reference. And then I will, for the first two courses, the reference will be the book on affine group schemes. And then I think I will use Borel's reference. Okay, so let's start. So let's introduce affine group schemes. So we are interested in a group of functors from rings. From rings to groups. Okay, so the notation is that for any ring R, GR is a group. And G also transforms maps between rings into group homomorphisms. And we fix, let's fix a base ring, a ring K, and restrict ourselves to the category of K algebras. So we say that a functor from the category of k-algebras to sets is said to be representable if there exists a k-algebra say A such that let's call the functor big F is isomorphic to the functor of homomorphism with source A. So it means that for any k-algebra, f of R is naturally isomorphic to the set of k-algebra homomorphisms from A to R. So naturally means that whenever you're given you're given a map between a homomorphism between two k-algebras. You have a commutative. You have the commutative square you guess, and okay. Okay, this diagram commutes. And an affine group scheme, the main object of interest for today is an affine group scheme. An affine group scheme is by definition a group functor from the category over K is a group functor from the category of k-algebras to groups which is representable. Okay, so this is the definition. It's a bit abstract. It's not even algebraic in some sense. It's not very much algebraic, but it comes from category considerations. And the first step, as I said, I want to explain under which condition you can say that such an abstract thing can be realized as a matrix group. Okay, because you can obtain affine group schemes by means of matrices. Namely, you start with equations over K on a set of matrices of given size, and then you vary the k-algebras and you look at the solutions in the various k-algebras. Okay, so this is so this tells you that from matrix consideration you can obtain affine group schemes. And today I'm interested in the converse. Under which condition on the functor can we say that such a functor is actually a group of matrices for any k-algebra? Okay, first let's provide some basic easy examples. The first one is the affine line. It's defined. It can be defined over rings. And it attaches to any ring. The additive group. The underlying additive group. This functor as a set functor is represented by the polynomials in one variable with coefficient in the integers, simply because a map from z of t to a ring homomorphism from z of t to R is completely characterized by the image of t. Such the possibilities are in one-to-one correspondence with the full set R. Okay, that's the first very basic example. The second example is the multiplicative group of dimension 1. One-dimensional torus. Well, it's defined also over Z, and it attaches to any ring. It attaches to it the multiplicative group of invertible elements in the ring. So this time it's represented by the Laurent polynomials with coefficients in Z. Namely, you can a map from Z of t and t minus 1 is completely characterized by the image of t, but this time you have a relation. In this ring, t is invertible, so the possibilities for the image of t only lie in the group of invertible elements of R. Are there questions? Check. Okay.
They after work set the identity to the
Yeah. Okay. The last example is the general linear group in any dimension n. Again, it's defined over Z. So you consider the functor which ends to any ring. The n by n matrices, invertible matrices, then it turns out that this functor is represented by a ring which has lots of variables. Namely, you have to introduce n square variables plus 1. But fortunately, there is only one relation, which is given by the determinant. We consider the matrix with coefficients, the variables, the first n square variables. And then saying that there is a trick to require that the matrix is invertible, consisting in saying that consisting in using this variable. So what you actually produce with this is, strictly speaking, is the following group. An element in the group functor. Let's call it is a matrix together with its determinant. Okay. So what I did in the example is that I gave you some I exhibited some functors which are representable and such that which go to the group to the category of groups, but there is no reason so far there is no reason why believing that sorry, I did not exhibited any algebraic structure on this algebra which could show that which could make you expect that the representable factor associated to this key algebra has a group structure for any ring. Okay, in the example it's okay. Okay, for any ring you can check that Gm of R is a group, Ga of R is a group, Gln of R is a group. It's okay. But now the question is, since I restrict when I'm dealing with representable functors, what are the algebraic consequences on the ring which represents the functor, which ensure me that I will get a group for any ring? Okay. So this is the notion of a Hopf algebra. Okay, so let me state the questions. What is the additional structure, algebraic structure? On A, such that the associated functor takes its values in the group, in the category of groups, for any K algebra. Well, first, why am I asking the question? Why can I expect this? Well, we can expect it in view of a well-known category result, which is called Yoneda's lemma. Why can we expect an answer? Well, simply by the following result, which tells you that you can completely describe in algebraic terms natural transformations between representable functors. So, more precisely, let EF be two functors represented respectively by A and B. Then there is a natural, natural correspondence, one-to-one correspondence between morphisms of functors between E and F and morphisms of K-algebras from B to A. So I simply sketch, give some hints of the proof. First, in one direction, if you starting with phi, a K-algebra map from B to A, free composition by phi provides a morphism of natural transformations for the functor between the functor E and the functor F. So natural transformation, as I said, is a collection of maps indexed by the K algebras, such that for any homomorphism between K algebras, this square commutes. So in this case, when I say precomposition, it simply means that given a K-algebra R, and given X in E of R, which is simply a homomorphism from A to R, then define phi R star of X to be X composed with phi. Okay, this is the correspondence in this direction. In the other direction, if you start starting with a natural transformation phi from E to F, sorry, yes, thanks. So this one goes to, thank you. So we have an element in E of A. We can see the identity of A as an element of in E of A, so that we can apply phi to this element. This gives this belongs to F of A, and this is an element from B to A. You can check that this provides the correspondence. Okay, so this is probably the most abstract thing that I will do today. So the point is to be convinced that if you are requiring is to realize that if you are considering things functorially, then you don't lose much, because the definition of morphism of functors is quite strict, in the sense that the condition to be a natural transformation with all these commutative squares is quite demanding, and actually can be turned into algebraic statements. Okay, so let's go back to the question. If this functor is takes its values in groups, what can we say about A? Well, the point, as you understood, we start with a functorial assumption. So in order to be able to say something, we have to turn everything, we have to turn the group structure into a business of arrows. Okay, so we have to see the group structure by means of arrows, by means of group homomorphisms. We have to turn the group structure into conditions, suitable conditions on arrows. Okay, so for instance, let G be an abstract group. What does it mean for it to be a group? Well, there is an element. So we first start to turn the unit element as a map. We see the unit element as a map from the trivial group to G. We have the multiplication. And the inverse map. So iota from G to G. And the group axioms actually can be translated into commutative diagrams, to which we can apply Yoneda's lemma. Okay, so let me first state the outcome. Affine group schemes are in one-to-one correspondence with a over K, affine group schemes over K are in one-to-one correspondence with a Hopf algebras over K. That is a Hopf algebra over K is a K algebra together with three maps which come from Yoneda. Well, abstractly we introduce them abstractly, but you see where they come from. Three maps. The first one corresponds to multiplication. It goes from A to A tensor A. Epsilon comes from the unit element seen as a map. And S comes from inversion, satisfying some conditions given by commutative diagrams. So the first one is associativity. Sorry. This diagram commutes. The next one comes from the identity, the existence of an identity element. No, it's badly written. So. And this is the canonical isomorphism between A and K tensor A. And then the existence of an inverse element sorry. Well, this map simply says that it sends it contracts the tensors up to modifying the first component by S. Okay. So if you believe in Yoneda's lemma, it's natural to expect an additional algebraic structure on an algebra representing a group functor. But okay, the price to pay is that this structure is not very pleasant to handle because it's quite complicated, but it's useful in some cases, and we will see. And today I will use it to show that eventually, after using all this business of commutative diagrams, eventually some suitable affine group schemes will be matrix group, and then I hope I will only use the matrix group point of view. Okay, so it's an instructive exercise to ask what are the maps delta S and epsilon in the examples I previously considered. For GA, check that delta is the map from V of t to Z of t tensor Z of t, which sends t to 1 tensor t plus t tensor y. Okay, I should simply say that for GM, okay, and S is the map which sends t to minus t. For GM, delta of t is t tensor t, S of t is t minus 1. For GLN, check that delta of xij is simply given by the formulas of matrix multiplication. And S of xij is given by Cramer's formula. Okay, so everything is it's a bit painful to to handle this kind of algebras. But if you want, it's very useful when you want to study smoothness of affine group schemes, for instance. And as I said, today it will be useful to show, to go to matrix, to the matrix point of view. Okay. So now let's precisely turn to this embedding result. Chevalez embedding theorem. So we keep the affine group scheme G. So it's represented, we know that now that it's represented by an algebra with the additional structure of a Hopf algebra. And we want to see that under suitable finiteness assumptions on A, the group G of R is a matrix group for any ring R. I will make this for any key algebra R. And we make this statement more precise. But let me first introduce later. But let me first introduce the vocabulary of representations, linear representations. So a linear representation for a group, for an abstract group, G. A linear representation is simply a homomorphism. Linear representation of G on some K module V is simply a map from G to the K-linear automorphisms of V. This is abstract, but now if you're given a K module, you can define a functor this is not so functorial at all, but given a K module V, one can define a group functor from K algebras to groups, which attaches to any K algebra the automorphism of R algebras of V tensor R. Let's call it GL of V and some argument. Okay, and now we can state functorially the definition of a linear representation for G, underlined G. So linear representation for underlined G is a natural map on V is a natural transformation from G to this functor. Okay, so it's demanding in the sense, so it's functorial, meaning that there is no algebraic geometry. This is the functorial point of view on algebraic groups. So one has to realize when one first sees this kind of business that the functoriality requirements are actually very strong, because you can take any. The requirement is that you have commutative squares for any key algebra R, possibly with key algebras which contains nilpotent elements and so on. So this is actually very strong. Strong enough to be equivalent to the geometric point of view on algebraic groups. Okay. So again, I played, you know, I will do the same as for the group structure. Namely, I have some functorial thing. This is a functor which is represented by some key algebra A. And what Yoneda told you is that maps natural transformations between between representable functors corresponds to maps in algebras, suitable maps between key algebras. Then there is a corresponding statement for this in the context of linear representations. Here it is. Let G be an affine group scheme over K, say represented by A. Then linear representations of G are in one-to-one correspondence with K modules B together with a map rho from V to V tensor A, satisfying two conditions stated in terms of diagrams. First, okay. This is better in fact. this diagram commutes. So as you recall that this map corresponds to multiplication of elements. So this simply says that, so you have to, if you want to have the set intuition, you have to reverse the directions of the arrows. So this corresponds to making act on V a product, and then, making the product of two group elements, and then making the product act on V. This is this map, this path. And this path corresponds to making act the two elements once one element in each step. Okay. This corresponds to the fact that G acting on H acting on V is simply GH acting on V. Okay, and then you have to require that the unit element acts trivially.